Okay. Now, Yusef, thank you. Excellent. Appreciate it. Now, so let's quickly, we did, in the last video, we have part 1 already done. This is going to be part 2. Hopefully, we're only going to make one more part unless something happens, okay? And I'm expecting a visitor. I may stop it and have a part 3, but other than that, we did compressibility, diffusion. We did a little bit on gas density, but I'll go over that. We did Charles' Law, effusion. I think that's about it. So let's start with, what was that? That was a ding. Let's start with partial pressures. Okay, what does it mean, partial pressures? What does that mean, the words together, partial pressures? Anybody? Anybody with me? Well, there was a fella by the name of John Dalton. You three, look up John Dalton and tell me something about his life when I call on you, okay? So get busy, the three of you. Okay, now, so John Dalton came up with something called the law of partial pressures. Anybody want to tell me about the law of partial pressures? Who had that? Law of partial pressures, that's at number 5. Who's group number 5? Okay? All right. Abby, what do you got? Abby is actually from Missouri. Wonderful state. It's called the Show Me State. That's correct, isn't it? The Show Me State. Excellent. I know the Arab students in class are looking at me like, what does that mean? Exactly. President Truman. Excellent. God bless all Democrats. Yes, Abby, what do we got?
Okay, Dalton's law of partial pressures states that at constant volume and temperature...
All right, this is what it states. You ready? At constant
volume and temperature.
At constant volume and temperature.
The total pressure.
The total pressure exerted by a gas.
A mixture.
A mixture of gases. The total pressure exerted by a mixture of gases at constant volume and temperature. Is that correct?
Yeah.
Yes.
Is equal to the sum of the partial pressure.
Is equal to the sum of the pressure of each gas.
Of the component gases.
Of the component gases. For instance, air. Air is made of predominantly nitrogen and oxygen, correct? But it's also made of things like argon, carbon dioxide. That about covers it. There are other trace gases. So if I measure just the pressure of oxygen, let me rephrase that. If I analyzed air, let's say the pressure of one atmosphere is 100 kilopascals. Yes? It's 101.3, but we're going to say it's 100 kilopascals, right? So if I said that the percentage of air that was oxygen was 20%, correct? What would the partial pressure of oxygen be? 20 kilopascals. Easy? Okay. If I said to you the percent of air that is nitrogen is 78%, what would the partial pressure of air be relative to nitrogen? 78 kilopascals. Right. Now, we know that 20 plus 78 is 98, correct? So therefore you could say that, what? What could you say? Argon and carbon dioxide take up 2%, or have a total pressure of 2 kilopascals, correct? Yes? Those values are a little fictitious, but they tell a story. And that is that each gas in a mixture of gases at constant temperature and volume impose on the system a pressure that is equal to the pressure of just each individual gas. And then you sum the pressures of each of the individual gases, and the sum of the pressure is the total pressure in the system. Make sense? Dylan, give me that, or Abby, give me that definition again. Just say it quickly, and I will because sometimes the sound is not picked up well. What do you got, Abby? Go ahead.
Dalton's law of partial pressures.
Dalton's law of partial pressures
States that at constant volume and temperature.
States that at constant volume and temperature,
The total pressure.
the total pressure
Exerted by a mixture of gases.
exerted by a mixture of gases
Is equal to the sum of the partial.
is
pressures
equal to the sum of the partial pressures
of the component gases.
of the component gases. Does that? I just felt I just said the oath of office for something, right? Does that make sense? That the sum of the pressures exerted by the components of the gases that make up a mixture of gases is equal to the pressure of the system. Make sense? Now, Dalton's law of partial pressures will come in very handy, and we'll talk about that hopefully before this review is finished. Okay? All right, so we talked about partial pressures. Okay? We talked about partial pressures. We talked about this before. We talked about diffusion. Okay, so Dalton's law of pressures, that should be partial pressures. Dalton's law of partial, that's really what we just did. Okay. Boyles Law, we talked a little bit about before. Just very simply, what is Boyles Law and who came up with it? Do we have anything on Dalton yet? You guys forgot. All right, let's get a different group here.
So slow.
Excuse me?
The internet's so slow.
The internet's so slow, I don't believe you. But
Well, it was a big part of atomic theory.
it was a big part of atomic theory. Excellent. So could you two put your heads together and come up with some information, not only on Dalton, but on Boyle right now? Go on. Now, so what is Boyle's law? We want to know the man behind the law, essentially, Ishmael. Yes, Fabiana.
Boyle's law, it states that.
Boyle's law states that. So this is a textbook definition. You know what? Put that away and tell me, Fabiana, put that away. Turn it upside down. Don't read it. You're trying to memorize it. But I want somebody to state, to the best of their knowledge, what they know about Boyle's law. Anybody? I don't want to hear a book definition. Joseph, what do you got? Just anything that comes to your mind. When you think of Boyle's law, what do you think of? I'm not asking you for the correct answer. I'm asking you for a portion of the correct answer. Pressure and volume. So when you think of Boyle's law, you think of pressure and volume. Excellent. What else do you think of when you think of Boyle's law? Anybody?
They are inversely related.
They are. I like that. Are all the people from Santander in Spain as good as you are in physics and chemistry?
Not all of them. Sir.
Not all of them, but many. They call Santander simply chemistry land, don't they?
Yes, they do.
Excellent. Okay. So, tierra de química. Okay, muy bien. Now, so Pablo said that pressure and volume are inversely proportionate to one another, or indirect. So meaning what?
If the pressure increases, the volume is going to decrease.
And vice versa, correct? Yes? Now we can represent that with a very quick formula. Pressure volume equals a constant. So let's say 1 times 10 equals K, right? So let's double the pressure to 2. What must I do to volume?
Divided by 2.
Divided by 2. You see that? Or if I say that this is 10, the volume must be 1. And how do you represent Boyle's law formula?
B1
Because,
equals
B2.
And I just did it here, didn't I? Didn't I do it here? So 1 to 10 equals 10 to 1, right? Didn't I just do it here? Did it all of a sudden click? Did it? I heard a click. I heard like 3 clicks. I like that. So Joe, you were frightened that you couldn't give the complete and absolute answer, could you? There was some fear there. I saw fear. Last time I saw fear like that was on a battlefield. Excellent. Excellent. So, but you just at least give part of the answer, right? When teachers ask questions, they don't necessarily want the whole entire answer. Just let's put this together as a class. And we did that with two people, didn't we? The Man from Santander. Sounds like a good movie, doesn't it? The Man from Santander. Okay? English subtitles. Okay, so Boyles Law of gases. Okay, let's look at another one. So we did that. Okay, what about Graham's law of effusion? What is Graham's law of effusion? And how would you represent it? Do we have any Graham's law of effusion people? Do we have any industrial applications? Do you have anything you want to talk about? Graham's law of effusion?
I have the definition from the book.
Is there more than just a definition? I'm not sure that we're looking just for definitions, are we? Is the Man from Santander going to simply give me a definition?
I can give you.
Is that what the world sees here? The world sees my class reviewing for gas laws, and you're just giving definitions? Where's the learning, man? Where's the love? I don't feel it, you know? Let's have some applications. What do you got for us? Let's start off. Go ahead.
Graham's law of fusion. States
Graham's law of effusion states that
the rate of diffusion of a gas.
the rate of effusion of a gas. So let's say the velocity of two gases is equal to,
Is inversely proportional to the square root of the gas molar mass.
the molar mass. Is that correct?
It is.
So what does that mean? Give me a interpretive statement. What does it mean?
The bigger the molar mass of a
The
gas,
bigger the larger the molar mass,
the smaller the rate of diffusion will be.
the smaller the rate of effusion. So what gas is numero uno? What gas is really fast? When you're thinking of gases, let's list some gases, shall we? Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, helium, neon. What else?
Hydrogen.
Hydrogen. What do you think would be the fastest gas and why?
Hydrogen.
Hydrogen.
Why?
Because it has a smallest.
Mass number 2. What would be next?
Helium.
Helium. Mass number 4. What's next?
Nitrogen.
Nitrogen. Mass number of 14. What's neon?
Okay.
Oh.
What's neon?
10.
Neon. What is the mass number of neon? Isn't it 20? 20, right? So that's going to be 14 and 14 is what?
28.
28, right? That's going to be 20. So would that be next?
Yes.
What's fluorine?
Fluorine is 19.
Fluorine is 19, but monoatomically it's 19, right?
38.
So it's 38. So what gas would be next? So it's this one, and then what?
Neon.
Then neon. Okay.
Nitrogen.
Nitrogen is 28.
Then
Then
oxygen, which is 32.
Oxygen is 32. Is that right? Is oxygen next?
Yes.
All right, then what?
Fluorine, 38.
Which one?
Fluorine.
Fluorine. Okay. And then it's easy from there, don't you think? Then it would be chlorine, bromine, and iodine. Now remember, bromine and iodine have to be in the gaseous phase, though, for that to be true, right? Right? Yes? Okay. So, what's the moral of the story?
The smaller the molar mass, the faster.
The smaller the molar mass, the faster it goes.
And then,
Faster it diffuses or effuses.
and then like real life application could be oxygen transport in the lungs.
Oh, I like that.
Or a balloon with helium or air. Which one is going to diffuse faster?
Well, I'll tell you something interesting. This is an interesting story. Is that my phone?
Yes.
Okay.
Sounds like something.
I don't know. You know what? This is a little weird. I'm cutting this off just to get the phone, but I'm not going to answer the phone. But it reminded me of something I want to do. Okay? Plus the ringing is driving me crazy. So I'm going to come back and we're going to do a part 3. And we're going to finish up, okay, and have a story. And the story is going to involve gases in the lungs, believe it or not, in plastic bags as well. Plastic bags. Look up the pore, the hole lining. How small are the holes in a regular, everyday plastic bag? Look that up, and we're going to talk about that on the next film, okay? Yes? We're off.